Okay, so we're going to evaluate the double integral over r of x, y, dA, where r is the region in the first quadrant bounded by y equals x, y equals 2x, and hyperbolas x times y equals 1 and x times y equals 2. After the semicolon, these are your transformations. And you know that because you have x in terms of v and u and y in terms of just u. So those have to be the transformations, or the transformation equations. So, all right. So in this one, it's not like where we have to name the UV transformation, right? Okay, so step 1 just reduces to finding the Jacobian here. So, and it is going to be the Jacobian of x and y with respect to u and v, which is what we want. Because remember, we set up the integral that we want over the region in the xy plane. We set it up in terms of u and v. We have that extra factor to account for the differences in area of the grid of rectangles you use to set up a Riemann sum. And so we want the Jacobian to be in terms of u and v because it's plugged into that integral. So what would that be here? So let's take the derivative of x with respect to u. So upper left-hand corner of your Jacobian matrix? Good. Negative v over u squared, right? Now let's take the derivative of y with respect to u. 1. Let's take the derivative of x with respect to v. 1 over u, right? Take the derivative of y with respect to v. 0. So the ugly negative v over u squared goes away when you multiply it times 0. So we dodged a bullet there. And then minus 1 over u, so negative 1 over u. Just remember when we plug it in the integral, take the absolute value. Everybody good with that step? All right. So step 2, ultimately in step 2 we want to find S, right? The region that we integrate over. So in order to do that, it's usually pretty handy to find R, to graph R. Okay, so here's 1, 1. Here's 0, 0. Y equals x will go right through those 2 points. So let me graph that. And then y equals 2x. We'll go through 0, 0 and 1, 2, right? Okay, and then we've got, believe it or not, x times y equals 1 is a hyperbola. It's kind of tilted from what you're used to, but if you think about it, you could write that as y equals 1 over x, couldn't you? So certainly that would go through 1, 1 also, wouldn't it? So let me use yellow there. So it'd go through 1, 1, and then what else? If I plugged in 1/2, it would go through 2, wouldn't it? Up here. And it kind of swings down like this. So that's y equals 1 over x. Would everybody agree with that? And then y equals 2 over x. You could write x times y as equals 2 as y equals 2 divided by x. So if you plug in 1, that guy goes through 2, doesn't it? Or goes to a height of 2. So 1, 2, it goes through. And then it's going to, so what's another point we could plug in? Well, it doesn't really matter. I know it's going to swing down like this. And then I can see my region is going to be this weird looking thing in here, which is definitely something you wouldn't want to integrate over if you can avoid it. Does everybody see how I got that region? Okay. So this curve in orange is, well, it might be easier to write it as x times y equals 2. And I'll write this one as x times y equals 1. And then this guy in purple is just y equals 2x. This guy in, I guess that's red, is y equals x. So that green region is R, and we want S. So let's think about how we could get that. So I'm going to set up my UV equations, well, my XY equations on one side, which I have, and my UV equations, which I want. So my XY equations, y equals x, y equals 2x, x times y equals 1, and x times y equals 2. And the idea is that these boundary equations, once you transform them using the transformation equations, they'll transform into the boundary equations of S. The boundary equations of R transform to the boundary equations of S. So let's start with, I think x times y, the x times y one is pretty easy. Do you guys see why? So look at the transformations. What happens if you multiply x times y, but in terms of u and v? X times y, you can see from the equations, the u's cancel, you just get v, don't you? So that makes v equals 1 and v equals 2. Does everybody see how I got those? Well, from this guy I encircled in orange here, those two equations are my transformation equations. And if I just multiply x times y together, multiply the left-hand sides together, well, okay, you have to multiply the right-hand sides together, and you just come up with v. And the reason I did that is because I was looking for what x times y equals in terms of u and v. In this case, just v. All right, so y equals x. Does anybody see a way to come up with that? The equivalent uv equation. So again, it's getting kind of messy here. We're focusing, we're going to use these transformation equations circled in orange here. Okay, so if y equals x, okay, what could I replace y with? U. And then what could I replace x with? V over u. And what's another way to write that? So I don't want another equal sign, that would be bad, but just maybe an arrow. So from that, I can get u squared equals v, or v equals u squared. Everybody buy that? Okay, and then I can do something similar for y equals 2x, right? It would be, y is u equals 2 times v over u. But that would be the same as? Yeah, or just u, let's see, 2v equals u squared for now. I might solve it for v, but maybe not. So these guys describe the boundary of S. The boundary of S. So let's graph them and see what S looks like. So now my horizontal axis is u, my vertical axis is v. So v equals 1 would just be a horizontal line, wouldn't it? So let's see. I'll call this line v equals 1. We'll say right there. So there's v equals 1. And then v equals 2. I'll do another red horizontal line for that. Call this v equals 2. Okay, so that takes care of these guys, but then we've got these guys, and we're going to have to think about this a little bit. Okay, v equals u squared. That's analogous to y equals x squared, right? If you think about it, because v is taking on the role of y, u is taking on the role of x. So just a parabola, right? With vertex 0 is 0. Now, we may not use that entire border, as you'll see. And I'll tell you how to determine what part of it we use and what part we don't. But I'll draw the whole thing for now. So I'll say that's 1 and that's -1. So the parabola will go through 1, 1 and -1, 1. And so that's v equals u squared. We may have to change that. And then 2v, okay, so 2v equals u squared, that's the same as v equals 1/2 u squared, right? So that one's just going to be a little shorter, isn't it? So we'll do that one in green, I guess. So at 1, it'll go, at u equals 1, it'll go through a height of a half, right? It'll still go through 0, 0. So something like this, I guess. And so it looks like there's two separate regions, doesn't it? Looks like there's this region and this region. But it's really only this region. How do I know? Well, if you look at R, I don't know what all of these intersection points are at the corners, but they're all positive, right? And the corners map to corners. That turns out to be true with these transformations. So if the coordinates of the corners are positive, and you've got transformations like x equals v divided by u and y equals u, those are going to transform positive coordinates to positive coordinates, right? So that's how I know, without a whole lot of thought, that it's got to be this region here, and it's not going to have anything to do with this region over here, because the u coordinates of these points here are negative, of those corner points there. Does that reasoning make sense? Yeah, so you can ease your worries if you think more simply, perhaps, than complex in certain situations like this. Okay, so take a look at this now. This region, really just focus on this region in here. I'm just trying to make it a little neater for you. You really need to think, okay, do you want to integrate, do you want to use a vertical rectangle to help you set this up, or a horizontal? Is it vertically simple or horizontally simple? It's not vertically simple. Does everybody see why? Because if I drew a rectangle here, the top of that rectangle is given by the curve in purple. If I draw it here, the top and the bottom changes, right? So it's not vertically simple. It is horizontally simple. So if I draw in a horizontal rectangle, no matter how I draw it, the left-hand end is going to be given by the curve in purple, the right-hand end by the curve in green, which, by the way, was this one, right? Or v equals 1/2 u squared. Okay, so that means which order of integration are we going with? So we're now to step 3 right here. We're going to set up the integral. Let's go ahead and put in our Jacobian absolute value of -1/u. And what does the integrand become? What was x times y? Remember, it was v, so that's pretty convenient. And then do we want to go dv du or du dv?
Du dv.
Good. du dv. Yep. That's analogous to dx dy, isn't it? Horizontal rectangles. Okay. So what does, so what do we have to do with these functions? It's got to be u in terms of v, right?
Mm-hmm.
So we've got to, what do we have to do here? Make it u equals positive square root of v, because that's all we're looking at here, right? And then we've got to go ahead and multiply both sides by 2, and then take the square root here. So what do we get here? U equals square root of 2v. Okay, so think left to right. The left-hand end of that rectangle represents the lower inner limit. The right-hand end represents the upper limit, right? Inside upper limit. So what do we get? On the interior, u goes from, well, wait. It's got to be the function in purple, right? But it's got to be square root of v, doesn't it? Okay. So square root of v to, so that's the square root of v to the square root of 2v. Is everybody with me on that? So if you understand that, then you're in good shape. Yeah. Why did we use square root of v for the lower limit? Well, because you got to look at the left-hand end of the representative rectangle, right? The left-hand end is given by the function in purple. Would you agree with that? And the function in purple if you solve it for u in terms of v, is the square root of v, right? So you take the square root of both sides of this. It's just like having x in terms of y when you have a horizontal rectangle, right? Same thing, because u is taking over the role of x and v is taking over the role of y. So in this case, u in terms of v. Does that make sense, you guys? Okay, then what does v run from? So v runs from 1 to 2, and there's your setup. To make it a little easier on the eyes, it's actually not hard to evaluate, so I'll leave that to you guys. But you're going to take the absolute value of this, so you just get v over u, don't you? du dv.